Yes. Not being seen there. Hello, was on that. I switch it on.
Only mic is on there. No. Yes, sir. PPT.
Yeah.
No.
Okay. Okay. It's charged, no?
Good afternoon, sir.
Good afternoon. Good afternoon. Which Namodaya you are speaking?
Jainvi Guntur, sir.
Genvik Guntur. Fine.
Yes, sir.
Okay. Okay. Fine. So shall we start? 2:30. Right?
Namaste, sir.
Namaste. Today is being the last day. We will try to do what best can be done for these two chapters, the D block and F block elements, and also coordination compounds. Right? Okay. Hope the things are moving on as per the period required, and the properties of D and F block elements we are talking about, right? Properties of D and F block elements. In the few of them that we have seen is the transition elements have high enthalpy of atomization. Transition elements have high enthalpy of atomization. High enthalpy of atomization, we mean delta HA. That is high. Why it is high? It is because of the enhanced metallic bonding due to the presence of unpaired electron. Right. Transition metals are paramagnetic, largely paramagnetic. We can say whenever we talk about this, they are largely paramagnetic. There is always an exception for every sentence here. So scandium salts are diamagnetic. What is the reason for that? All scandium salts are 3+ oxidation state. Scandium in 3+ oxidation state is having D0 configuration. Its 4s2 electrons outside is paired. So therefore it is diamagnetic. Zinc salts are diamagnetic. Okay, zinc salts are diamagnetic because it is D10 configuration, right? So this way you have to answer and pick up the technical term through which you can able to explain, and while writing this you underline that. That is the best way. That is the best way, right? Okay, now this is a complex. They form the complex ions. These transition elements are forming complex ions. What is this complex ion is? Complex ion, we have come across such kind of substances, right? K4FeCN6. Okay, this is a complex. So here what we find is transition element. Mostly the transition elements form many number of this kind of complexes. Here this is a complex entity. This is a complex entity. FeCN6 4-. This is a complex entity, right? So why they could able to form this complex entity? So this is the point. Now Fe, the transition elements, they have small size. That is one of the reason is they have small size compared to the other metals. What we mean is they are having high ionic charges. High ionic charges. These are the two important reasons why they show complex formation. They show tendency to the complex formation because of these two things. High charge on the transition ion, high charge. Okay, when the two electrons are lost, their radius is smaller. Whenever they are having high charge, what we mean is they can able to attract the given pair of electrons from ligands more strongly. Therefore, they are. This is the one which key point by which the transition elements show complex formation. The availability of d orbitals. Another thing is availability of d orbitals, empty d orbitals. So whenever orbitals are available, so that ligands can give the pair of electron. Okay, ligands are those species which will give a pair of electron to the metal atom or ion. So when a metal ion to receive that, it should possess empty orbitals. For the empty orbitals, this transition elements have that. Therefore, it is going to. Now, which are the complexes well known? So this is the, of course, you are doing it in the salt analysis also. Suppose if it is copper is given, copper 2 plus ion, which is blue in color. So we are adding NH3 to make it sure that whether it is copper ion, so that it will form a complex with ammonia. Ammonia acts as a ligand, and it becomes deep blue colored. You can see the change here. The blue colored copper ion will become deep blue colored one. This deep blue color is because of the formation of a complex. Copper forms such a complex, right? And you know that silver chloride AgCl is white in color. It is a precipitate. When chloride ion you want to find out, what you do? For the chloride ion, you are adding AgNO3, so that AgCl ion is AgCl precipitate outs. When AgCl precipitate outs, to confirm that it is AgCl, you are adding NH3. So in NH3, it is soluble. So the white colored AgCl will be soluble in ammonia. Again, it forms a ammonia complex with ammonia. Okay, so this is the way that the complex formation is there. You see the video so that we can able to understand more about it. These are the transition elements. So this is what the complex which looks like. There is a central atom. So there is a central atom or an ion, right? These are all ligands, and these are anions, counter ions. The anions are counter ions, and the neutral molecules like ammonia can be ligands. They are called ligands. Okay, so they form a complex, and they will be having certain geometry. Always they will be having a certain geometry for that, right? So pentaamine cobalt 3 chloride, potassium ferrocyanide, what I have written earlier also, nickel tetracarbonyl, all these are the complexes which are formed by transition elements. Okay, so these are called complexes, and they are also having counter ions which is linked by ionic bond, right? So this complexes formation is because of the number of protons here in the metal is high, the high positive charge of the transition elements, high positive charge. Okay, so this is how they can able to form, and also because of the vacant d orbitals. If the orbitals are not there, if the vacant d orbitals are not there, what they are going to do is, if the vacant orbitals are not there, they are going to make use of the orbitals which are further. Okay, so if d orbital is completely filled, then it uses S next to p orbital and next to d orbital. Okay, so suitable hybridization takes place, and accordingly the pair of electrons donated by ligands are accommodated. So this is how the complex formation is possible. So the complex formation, why they form complexes? For this answer is, the transition elements, they have small size, high ionic charge, and presence of empty d orbitals. So these are the three reasons that we can give. Now, another property is catalytic property. They show the catalytic property. So which are the catalysts that we have used? So we used platinum catalyst in the presence while preparation of nitric acid, and in the Haber's process is preparation of ammonia. We need Fe as catalyst. So these are transition elements. Not only the elements, their compounds. For example, vanadium pentoxide, V2O5, is acting as a catalyst when it is in the contact process of preparation of sulfuric acid, V2O5, vanadium pentoxide. This acts as a catalyst. Therefore, elements, transition elements or their compounds are used as catalyst. And in hydrogenation of oil, we use nickel as a catalyst, right? So what could be the reason for this? Let us try to explore this. Okay, this is due to the presence of unpaired electrons in the and incomplete subshell. Incomplete subshell is one of the things, one of the reason, not the whole sole reason. This is one of the reason. Why this unpaired electron, presence of unpaired electrons has to do? Presence of unpaired electron may do some temporary overlap with the orbital or a compound which can be unstable before the product is being formed, right? So they are holding the reactants in their place so that they make ease of the process. Let me tell you more about it. Variable oxidation state of transition metals is the ability to form complexes. Okay, variable oxidation state, presence of that also is a reason. For example, V2O5 is the one which is used for conversion of, this is being used for conversion of SO2 to SO3. Sulfur dioxide to sulfur trioxide, we need a catalyst V2O5. So naturally available oxygen, if it is done also, it at the higher temperature also, it is not easily done until we use V2O5. Now V2O5, why V2O5? Because it has got variable oxidation state. Now SO2 reacts with O2 V2O5 and forms SO3 plus V2O4. This V2O5 can give one oxygen so that it forms V2O4 because vanadium with +4 oxidation state also is also available. Then later this V2O4 takes an oxygen and form V2O5 back. So catalysts are regenerated in the process. Therefore, the variability of the oxidation state helps us to make this conversion possible, easily possible. Therefore, variable oxidation state is also one of the reasons why transition element compounds can used as a catalyst, right? And another thing is they provide large surface area with free valency, right? What is meant by this? So this is what we mean is adsorption. What is this adsorption? Adsorption means attracting and retaining in the surface. Once they are attracted and retained over the surface only, then it is called adsorption. The surface of the metal is suitable for adsorption. Okay, so that interlocking system, what is present in the radius of the atom, that will help that. We will see the video and so that you can able to understand more, right? Okay, so here it is the preparation of ammonia. This is iron, nitrogen, hydrogen get attracted, nitrogen and hydrogen get attracted, and when nitrogen and hydrogen get attracted, they will be on the surface because of adsorption. When they are in the surface, their concentration has increased because gaseous phase they are all not close, they are far away. But when they get attracted, they are nearer. So they get attracted, they are nearer. When the concentration is increased, you know that from the chemical kinetics, when the concentration is increased, the rate of reaction increases. Therefore, this is going to happen in that way. So adsorption helps in increasing concentration, thereby the rate of the reaction increases and catalytic properties because of this adsorption. So for that, it should provide the large surface area available for making it adsorb, right? Okay, right? We'll see the, okay. Look at this. Nickel is used for unsaturated hydrocarbon to a saturated hydrocarbon. Okay, H2, addition of H2. Preparation of ammonia, we have taken Fe, right? And Ostwald process, we need nickel. It is all because of the catalytic property is because of the multiple oxidation state. As we have discussed all this, multiple oxidation state makes this possible. So this is how the metal surface is looking like. The surface attracts the surface, attracts the substrate, and it is being formed. So this is a schematic diagram of contact process in which sulfuric acid is being produced. Contact process, right? Haber's process in which we get ammonia, nitrogen, and hydrogen needs to be passed to get ammonia. And this is hydrogenation of oil. Right. So when hydrogen get attracted, when this attracts hydrogen, wherever double bond is there, it gets hydrogen, and metal is having greater affinity to the hydrogen. The small atom, that will be get absorbed very easily by the metal surface. Hydrogenation of oil, that we use it, right? So these are the reasons for why they are used as catalyst. Okay. Chlorine production with HCl oxidation, we use copper sulfate as a catalyst. Sulfuric acid, by contract process, we need V2O5 or platinum. Fat hardening, nickel. Nitric acid by NH3 oxidation, platinum and rhodium catalyst. We use. These are the different catalysts we use. These catalysts are from the transition elements. Okay. Now, another property that we see from the transition element is they form interstitial compounds. What are that interstitial compounds? Interstitial compounds are formed when the atoms of the metal in the lattice, this is the lattice of metal, the voids present here are being occupied by some other atom. The small atom. The small atom may be boron, hydrogen, or carbon, right? In case of steel, the carbon particles go inside the voids of the iron. Therefore, it is giving the better property than iron in terms of hardness, and also it will not get rusted soon. And such interstitial compounds are being formed. Why they are forming such kind of interstitial compounds? The reason is they are having such a large void area. So in that, small atoms like hydrogen and boron or carbon can be inserted. Hydrogen, boron, carbon can be inserted. So are they compounds? Even though it is called as compounds, it is not a compound actually, it is a solution. In a compound, what is the ratio of the atoms combining must be fixed, right? Law of constant proportion is to be followed, right? In case of the formation of a compound. But by the way, naturally it has come as an interstitial compound, but it is actually solution, interstitial solution, right? Now this is the lattice in which the small atoms can occupy, and such one is called interstitial compounds, right? Yeah. Look at this actual. Yeah. This is how the metal is present, right? So these are the voids. And in these voids, there can be small atoms like boron. Many of the interstitial compounds show the better hardness. They are hard and better property. Okay. Smaller atoms occupy, but not in the ratio, not in the fixed ratio. Okay. Not as copper sulfate pentahydrate or hydration has got some constancy. 1 mole of copper sulfate attracts 5 moles of H2SO4, but it is not having that. Non-stoichiometric compounds, they are called non-stoichiometric compounds. You can see here Fe 0.94, oxygen 1. For 1 oxygen, Fe is 0.94. Okay. And titanium carbide, okay, and manganese nitride, all these are interstitial compounds. Titanium carbide is a special compound. Its hardness is equal to that of diamond, which is considered to be the hardest substance. And this is interstitial boride compound, hard like diamond, like. Okay, so it looks like this. And I will tell you, to show you about the titanium carbide. Yeah, this is titanium carbide, right? Melts at 3683 Kelvin. See it, where it is used. It is used in the tips of the lathe machine. Lathe machine in the sense where you have to drill a hole in a metal sheet, like, okay, very hard substances where the drill is to be done, then such kind of materials which are used, titanium carbide, okay, and titanium nitride. These are all interstitial compound and show great hardness, right? So this is another property that we see is they do alloy formation. They form alloy easily. So many alloys are known. Transition elements, for example, brass, bronze, right? German silver. All these are the alloys. Alloys, what are alloys? Alloys are homogeneous mixtures, right? Homogeneous mixtures of metals. So metals in the liquid state, they are mixed, right? And why they are forming alloys so easily? Transition they can be exchanged. One atom in the lattice can be replaced by the other easily. How it is possible? It is because the size is more appropriate. They are having, many of the atoms are having only about 15% variation in their size. Okay. Therefore, wherever one atom can be replaced by the other, this alloy formation is possible. Okay. Brass, you have seen the brass, right? The bronze metal, right? All these are the better metals. Okay. We'll see. Okay, mechanical property, deformation of metal, sensitivity of metal, less resistant to corrosion, and cannot withstand thermal stress. Okay, all these mechanical properties that we can have, the metals, these alloys overcome this. More stiffness, unlikely to break, lighter in weight, more resistant to corrosion, high strength to weight ratio. Okay, these are the things, right? So when you want to make homogeneous mixture, they should be added in the liquid form. The metals are to be added in the liquid form, right? So the industries where the metals alloys are to be prepared, they will heat in that way, and they will mix it, right? So because these are the size do not vary much, they transition elements do not vary in the size, one can be easily replaced by the other, right? So this is how alloy formation is easily possible. Okay. Let us look into different alloys, types of alloys or different alloys. Okay. Okay, ferrous alloys, mainly ferrous alloys and non-ferrous alloys, because large number of ferrous iron compounds are known. Iron with carbon, okay, with only carbon, this is called steel. And chromium, vanadium, tungsten, molybdenum, nickel, with all. Stainless steel is an alloy, ferroalloy. It is a ferroalloy. Okay. Okay, carbon is less than 0.1%. Okay, then it is called iron alloy, carbon. So if it is less than 1%, then this is called wrought iron, iron with less than 0.1%. Okay. So steel iode, this is vanadium steel. You have come across all these things, chromium steel. When you add chromium and nickel, it will get that glitterness. Okay, smooth surface, glittering surface you can see. Okay. Self-explanatory, doesn't contain iron. These are all non-ferrous ions, right? Okay. So these are the different alloys which are being formed and we are using daily. Formation of oxides. Okay, now coming to the chemical property of that. So they form oxides. They form oxides, and the metallic oxides. Metallic oxides are normally to be basic in nature, right? Sodium oxide is basic in nature. When it put in water, it becomes sodium hydroxide. You know that. Okay, transition metal forms oxide. General composition is MO, M2O3, MO2 or MO6. This is the general way they are present. And lower oxidation states are only basic. And higher oxidation states are amphoteric or acidic. This is an important point. So an acidic metal oxide can also be acidic. A metal oxide can also be acidic. Mn2O7 is acidic. These are amphoteric in nature. Even this with the chromium, it happens so. Cr2O3 is amphoteric. MnO is basic. MnO, here it is having +2 oxidation state. Right? Here manganese is having +3, and this is 3/4. Okay, this is 3/4. It is a fractional one, and MnO2 it is 4, and here it is 7 +7. And you find that when the oxidation state increases, the oxide from basicity to acidic oxide it happens. What could be the reason for such kind of change? When the metal loses more and more electrons, it becomes so small. The cation becomes very, very small, right? Suppose if it loses 7 electrons, then automatically the number of protons will remain same. Because of this, there is a large attraction, and such an attraction that it becomes so small. Polarization occurs. So smaller metal ion can do polarization, right? Polarization is a non-metallic character. So non-metals are small in nature, right? Non-metals are small in nature. Okay, so their oxides are acidic in nature, and they also turn into a small size. This is one reason, and the polarization is gives the covalent character, an ionic character to covalent character, shift of that. Therefore, it behaves like a non-metal, or it behaves like the acidic oxide. It becomes an acidic oxide, right? Right, what you have learned is transition elements, D block elements, and transition series, 3D series, 4D series, 5D series. About that, general electronic configuration, trends in the properties, okay, and general characteristics that we have seen, right? So this is about the general property of transition elements, right? Okay, now coming to the next part of it, right? Okay, next part of it. In the D and F block elements, there are some important compounds of transition elements. There are important compounds. So as you know that, we are going to study about the two compounds, K2Cr2O7 and KMNO4. KMNO4. Okay. So some compounds which contain oxo anions. They have selected the two compounds which consists of oxo anion. Which is the oxo anion present here? Cr2O7 2-. This is the oxo anion. Oxo anion. And here this is MnO4-. Permanganate ion. This is called permanganate ion. This is dichromate ion. Okay. So how do we prepare what are the properties of them? They are all oxidizing agents and normally used in the laboratories as an oxidizing agent. Therefore, this is there added in the syllabus of it. Now, potassium dichromate. Okay, this is what we are going to know. Potassium permanganate, methods of structure and the structure of them and all this. Yes, this is how it looks. Potassium dichromate. Potassium dichromate. This is how it looks. Okay, how it is to be prepared? It is prepared from chromitor. Chromitor FeCr2O4. Chromitor is FeCr2O4. Okay, available in the earth crust. And this chromitor is fused with sodium carbonate and oxygen and heated, roasted. It is roasted. So it forms sodium chromate. Na2CrO4 is sodium chromate. And iron oxide, FeO, is converted into Fe2O3. Higher oxidation state. That's what. FeO is converted into Fe2O3. Okay. Then now Na2CrO4 is to be converted into sodium dichromate, Na2Cr2O7. So sodium chromate, when you add sulfuric acid, acidification, it will be converted into sodium dichromate. Sodium dichromate and sodium sulfate and water, right? Second step. And the third step, this sodium dichromate is converted into potassium dichromate. This is what we are by mixing with KCl, potassium chloride, right? So this is how we are going to get potassium dichromate. Okay. So you remember the few things. Remember the few things. Okay. The steps. FeO Cr2O3. So this combination is chromitor. We may write like this, FeCr2O4 also. This is chromitor, FeCr2O4. It is a combination of FeO plus Cr2O3. This is chromitor. The first step is with sodium carbonate, fusing with this, you are going to get sodium chromate, Na2CrO4. So practice this first.
Sir, no video, sir.
Oh, fine. When it has happened. Yeah. It might have happened on its own only. Right? I don't know. Somewhere it has. Okay. Yeah. No, just now it might have happened, no? Right. Okay.
Home assignment is the slide. Home assignment.
Okay. Yeah. Okay. I think this about this slide, whether you could able to see this slide. Whether should I
Yes,
start
sir.
from here? Yeah. This is potassium dichromate. This is how it looks like. Potassium dichromate. And this is prepared by using chromitor. Chromitor is FeCr2O4. FeCr2O4. Right? So how it is to be prepared is chromitor is fused with sodium carbonate and oxygen and roasting. Okay, roasting is being done so that it is converted into sodium chromate, Na2CrO4. It is yellow in color. Now Na2CrO4, when it mixed with sulfuric acid, we get sodium dichromate. And sodium sulfate and water. Sodium dichromate, Na2Cr2O7. Now, When sodium dichromate with KCl, it will give K2Cr2O7, potassium dichromate, right? And NaCl. So there are three steps. There are three steps. Remember it like this. When this particular chromator, FeO plus Cr2O3, this is chromator, right? This is fused with sodium carbonate and oxygen and roasting. What you are going to get is Na2Cr O4, sodium chromate, right? Then sodium chromate, when mixed with sulfuric acid, we get sodium dichromate, Na2Cr2O7 plus Na2SO4 plus H2O. These are the other products. But remember these things importantly. Then Na2Cr2O7 on addition with KCl, we get K2Cr2O7, potassium dichromate plus NaCl. Okay. The orange colored K2Cr2O7 is obtained by using Na2Cr2O7 with KCl. Right? This includes three steps. Major products, first try to remember, then practice a bit, and then write the other products also. Okay. So it is possible to remember. This is one of the preparation or the properties, one that oftenly asked question. Now, what is the property of potassium dichromate? So it is an orange colored solid. It is sparingly soluble in water or cold water. In the hot water, it is freely soluble. It melts at 398 degrees Celsius, right? K2Cr2O7 and Na2Cr2O7. There are two things, K2Cr2O7, Na2Cr2O7. This is preferred. K2Cr2O7 is preferred because Na2Cr2O7 is hygroscopic in nature. Hygroscopic means it absorbs moisture. Okay, whenever we want to use it in the volumetric analysis, if it absorbs moisture and it changes its concentration, then it cannot be used at all. Therefore, it is K2Cr2O7 is being used, right? Effect of pH in the potassium dichromate, right? So this is what the color of potassium dichromate is, orange color. This is converted into this yellow color if you add base to this. Potassium dichromate, if you add base, it will become yellow colored, right? So yellow CrO4 is O4 2- is yellow color. This is orange colored, right? Or reverse way also you can do. You can take this potassium chromate ion and acidify this. You are going to get potassium dichromate, orange color. This change you can do by varying the pH value. When you get this, add H plus ion, and when you get this, you add a base so that it is interconvertible, right? At pH 4, it is a equilibrium and we cannot distinguish. Okay, powerful oxidizing. Okay, this is a powerful oxidizing agent in the acidic medium. This is a powerful oxidizing agent. Dichromate ion is written like this, Cr2O7 2-. In the presence of an acid, it gains electron. It gains electron means it is undergoing reduction. It is undergoing reduction means it is an oxidizing agent. So potassium dichromate is an oxidizing agent. The key thing to note is Cr2O7 2- is converted into Cr3+. Okay. So what all it oxidizes? It oxidizes ferrous ion, Fe2+ ion to Fe3+ ion. Right? It oxidizes iodide ion to iodine. Iodide ion to iodine. Okay. Stannous, Sn2+ ion to stannic, Sn4+ ion. Okay. This is the ionic form. You can write the equation. Right? It converts H to S into sulfur, hydrogen sulfide into sulfur. Okay, so sometime you will be asked to write such equations. Okay, properties. Okay, write the chemical reactions of, okay, potassium dichromate with, okay, then you can give such ionic equation. Okay, few things you have to remember. Okay, few things that you have to remember, right? That is Fe2 plus ferrous ion is always converted into ferric ion. You have to remember this. Iodide ion is converted into iodine in the acidic medium. Okay, so these things, what I told you, ferrous ion to ferric ion, iodide ion to iodine, stannous to stannic, SN2 plus to SN4 plus. Okay, so this you have to remember. I tell you how to write the balanced equation because it needs balanced equation, writing of balanced equation in this case. Okay, now you know that dichromate Cr2O7 2 minus dichromate ion in the presence of H plus ion, it takes some electron, and what is the product? This is giving Cr3 plus chromium ion plus H2O. This is Cr3 plus ion, right? So this half reaction that you have to remember, that is suitable for, this is required for writing equation for all this. Okay, for any of this, if you want to write the equation, you need to remember this. Dichromate ion will give Cr3 plus ion, right? Now let us balance it by using the 11th class, what we have learned, balancing of redox reaction. Chromium is having +6 oxidation state here. Okay, +6 oxidation is converted into +3 oxidation state. So any species converting +6 into +3, that needs 3 electrons. But here Cr, we have to balance first chromium atom wise, then 2 chromium ions of +6 stage. In order to form 2 Cr3 plus, then 6 electrons are needed. Pardon me? Any doubt?
सर वीडियो नहीं दिख रहा है.
अरे, it's automatically getting. Yeah, it is getting off automatically. Why? Okay. Okay. Is it okay now? Okay. Okay, I think this is not the one. Yeah. Okay. Okay. So I was talking about how to balance this. Again, I have to write. I will write here. Hope it is visible now. Right? Cr2O7 2 minus plus H plus electrons giving rise to Cr3 plus H2O. I am reminding you how to balance this. First, balance the atom. 6 plus 2, 3 plus 3 electrons needed. 2 such atoms are there. Therefore, 6 electrons. 2 minus charge and 6 minus charge. Totally 8 minus charge. Here it is 6 plus charge. Therefore, this is 14H plus is needed. 14H plus will make the charge equal. Okay. 2 minus 14 plus 6 minus is nothing but 6 plus, which is there in the other side. Right. Now, 14H plus means it is 7H2O. Now hydrogen and oxygen both are balanced. This is the way you have to balance, because why I'm telling you all these things is balancing this redox reaction is required. You have to write the reactions in the balanced form only. Inorganic comes in. Organic you can ignore, but here you have to balance. Right. Suppose if you want to write Fe2 plus is converted into Fe3 plus. Fe3 plus, then it happens by losing one electron. In the half equation also the charge is balanced, right? Now you can write the overall reaction by multiplying this by 6. Multiply this by 6, right? So this is the way you can able to write the balanced equation. Okay. Okay. So 6 Fe2 plus, you can see it is multiplied by 6. 6 Fe2 plus, 6 Fe2 plus, 14H plus. Okay. All these things are correctly done. Therefore, take some examples and practice. That is the best method to write any equation given in a perfect way without mistake. Right. Now, use of potassium dichromate, as it is a volumetric analysis we use, right? Volumetric analysis we use. The estimation of reducing agents such as oxalic acid, ferrous ions, iodide ions, for this we are using in the laboratory, right? If you have already come across the volumetric analysis, in the volumetric analysis, we have used potassium permanganate with oxalic acid. Even potassium dichromate titration also can be done in the same way, right? And tanning, some industries also we use this. Calico printing and photography, we use this potassium dichromate, right? Now there is one called chromyl chloride test. Chromyl chloride test. Okay, this is not meant in the it is not necessary for you for the theory, but practically when you do the analysis of chlorine, or chlorine, you are finding out chlorine radical in the salt analysis. Whenever you are analyzing, this test you are doing this test for the confirmatory test of chloride ion. It is called chromyl chloride test. It is called chromyl chloride test. Salt plus potassium dichromate you are using. Potassium dichromate you are taking, orange color substance, and you are adding concentrated sulfuric acid. Concentrated sulfuric acid, it gives brown fumes. You can see the brown fumes. Okay, when your concentrated sulfuric acid is added, it gives brown fumes. Then brown fumes is to be passed through the solution. Okay, if it is lead is the one which is present in the salt, lead, it will give, okay, lead chromate. Okay. Okay, it is a confirmatory test for that lead. Okay. So this is the way that we have to pass. When enough is passed, you can shake that so that we will get the orange red precipitate. It is only the CrO2, Cl2. So in the organic chemistry also, we have used CrO2, Cl2. This is in the Itard reaction, benzene to benzaldehyde, right? Okay, with lead acetate, when the lead acetate is added, okay. Okay. Okay, we'll get the thing right. Okay. Fine. So this is the way that we do chromyl chloride test. And this is the potassium permanganate. Another one compound for the preparation is potassium permanganate. Potassium permanganate, even though it looks like black here, it is purple in color, right? So for preparation of this, we need pyrolusite ore. Pyrolusite ore is MnO2. Okay, it's pyrolusite ore is black in color, MnO2, right? So when MnO2 is fused with, again, this is to be fused, similar process with KOH and O2 and roasting needed, heat is needed. Okay, MnO2 is a solid, KOH, oxygen and heating, you get K2MnO4. What is this K2MnO4? Potassium manganate. It is potassium manganate, right? So potassium permanganate is KMnO4. Potassium permanganate. Okay. And here it is K2MnO4. We have not got the product. It is potassium manganate. We are getting potassium manganate. When potassium manganate, okay, so this is how you can able to write that. MnO2, MnO4, 2 minus ion. This contains MnO4, 2 minus ion, whereas this contains MnO4 minus 1 ion. Okay. Now this MnO4, either acidification or you can use Cl2, chlorine, to get potassium permanganate. Potassium permanganate. Okay, if you use Cl2, then potassium permanganate and KCl are formed. This is how you can, and it is also having that property of conversion of in the different pH. I will show you about that. Okay, this is the property, is a crystalline compound and sparingly soluble in water in the room temperature, slowly soluble, sparingly is okay, and it is in the high temp in the temperature, more temperature, it will be soluble readily. KMnO4 gives oxygen. Okay, it is a method of preparation of oxygen in the laboratory. Potassium permanganate is heated to get oxygen gas. K2MnO4 and MnO2 are the other products. So this is how the pH, the change of the pH. Potassium permanganate is purple color, MnO4 minus. And if you add a base, then it becomes MnO4 2 minus, manganate ion. Permanganate ion becomes manganate ion. And reverse is also possible. This change of this color, you can do this and you can try in the laboratory. Okay. So again, KMnO4 is a strong oxidizing agent. KMnO4 is strong oxidizing agent, right? This is oxidizing agent in a different medium. You have to remember, in acidic medium, it is an oxidizing agent. In alkaline medium, it is an oxidizing agent. And in basic medium, it is an oxidizing agent. Why we have to say all these things? Because separately, it is because MnO4 minus ion in acidic medium will give Mn2 plus ion. The products are different. The same MnO4 in neutral medium or slight alkaline medium, it will be giving MnO2. And if it is an alkaline medium, MnO4 will be giving MnO4 2 minus, MnO4 2 minus. Okay. So the changes in a different medium are there. You have to remember these two. Okay. Slightly alkaline medium or in neutral medium, also it acts as an oxidizing agent. Okay. Now, so in neutral medium, it will take only 3 electrons. In acidic medium, it takes 5 electrons. So conversion is different, and half equation that you have to remember for writing all the reactions. What are the reactions of it? Right. Okay, in acidic medium, this is the one that we are taking. Since it takes 5 electrons, its equivalent weight is being found out in this way. Molecular weight divided by 5 electrons. For an oxidizing agent, how much number of electrons it takes, okay, for getting itself reduced. Okay, that is the number to be divided. So that we'll get equivalent weight of KMnO4 in acidic medium. Now, it changes, okay. It has next one actually, okay. It changes ferrous ion into ferric ion, iodide ion into iodine, hydrogen sulfide into sulfur. Sulfur dioxide is oxidized to sulfuric acid, right? nitrite ion into nitrate, oxalic acid into carbon dioxide. Okay, so these are the reactions that you have seen, and this is the one which you have seen in the practicals. Oxalic acid versus KMnO4 or Mohr salt. Mohr salt is consisting of Fe2 plus ion. So this oxidation reaction you are supposed to remember even in the practicals also. You are supposed to write the ionic equation or the complete equation in the examination. If it is asked, and it is most likely to be asked, right? So iodide ion to iodine ion. Okay. So remember that. So this MnO4 is converted into Mn2 plus ion. Okay. So like that. In basic medium or slightly alkaline medium, or you can say in the neutral medium, it changes iodide ion, not as iodine, it changes into iodate ion, IO3 minus ion. So the way it changes is different, iodide ion to IO3 minus ion, and MnO4 is converted into MnO2. So you note the differences and practice the equation. That's only the way that we can do. MnO4 ion in basic medium or the neutral medium converts thiosulfate ion, S2O3 2 minus thiosulfate ion into sulfate ion. So two reactions. When I say basic medium or neutral medium, there will be two equations that is given in the textbook also. These two. Okay. So these are the things to be remembered and practiced, right? So what is the half equation? MnO4 minus ion in acidic medium, H plus, receives electron to form Mn2 plus H2O. Remember these things. Okay. Then balancing is also easy. +7 oxidation state, +7 to +2, 5 electrons. Right, 7 to +2, 5 electrons it has to receive. Now -1, -5 plus -6, -6 to, okay, -6 to +2. Therefore, it should be 8. 8 plus and 6 minus is 2 plus. Now 8H plus ion should be 4H2O. So this is the way you can balance, right? You can balance the half equation. Remember, here it is Mn2 plus. Mn2 plus. Okay. So these are the key things that you have to remember, right? It is used as a laboratory reagent in industries. Alkaline potassium permanganate is Bayer's reagent. Alkaline potassium permanganate in the dilute solution of Bayer's reagent. It is used for testing unsaturation. Okay. So the unsaturated compound, if you add it, it becomes colorless. KMnO4 is get colorless. Okay. So manufacture, it is used in manufacture of saccharin. Okay, artificial sweetener, saccharin, benzoic acid and acetaldehyde. We use KMnO4, right? In the organic chemistry, we are using that KMnO4H2SO4
Sir, video is not visible.
oxidizing agent. Huh?
Video is not visible.
Yo, it's happening. I don't know why it's happening. It's just, it's happening on its own. Okay, fine. At the end, you see, look at the structure of these ions, right? This is the structure of chromate ion. This is dichromate ion. Chromate ion, CrO4, 2 minus. Charge is 2 minus. Chromium with 4 oxygen with single bond. Okay, 2 oxygen with double bond and 2 with single bond. Chromate ion. Dichromate ion. Okay. So there are 4 oxygen atoms you can see surrounding this chromium and 4 oxygen atoms surrounding this. Oxygen takes both the CrO3, right? In this way, the dichromate ion is being present. So manganate ion and permanganate ion. Okay, tetrahedral, both are tetrahedral, but this is green in color and this is purple in color, right? Okay, this is the thing, right? Something happened. Your default microphone has changed capture input. Okay, fine. Hope everything is clear. Okay. Yeah, again, once again, being changed. I don't know why it is so. Right. Okay. Okay. We are moving on to another part of it, that is D and F block, inner transition elements or F block elements, right? F block elements. Okay. So in this, we are going to know about general electronic configuration, general properties of inner transition elements, lanthanoid and actinoid contraction, important. Then properties of lanthanoids, actinoids, and their differences, right? Inner transition elements, the F block elements, they are present as a separate block in the periodic table. Last electron enters into the F subshell, so they are known as F block elements. There are two rows of 14 elements each. One is lanthanoid, which is followed by lanthanum, and actinoids, which followed by actinium. Okay, lanthanum uses 4f orbitals and they uses 5f orbitals. Actinoids uses 5f orbitals. Okay, so these are the little lanthanoids. Okay, so supposed to be here and they are all kept here, lanthanoids. Now coming to general electronic configuration. General electronic configuration of lanthanoids, 4f1 to 14. I have talked about it in the beginning also. 4f1 to 14, 5d 0 to 1, because they have the tendency to get stabilized, half field stability or full field stability. They will push the electron, right? Thereby, that is the electronic configuration that we have to write. Last electron enters one of the 4f orbitals, so they are known as F block elements. Okay, so these are the basic things. Lanthanoids are from cerium to atomic number 58 to lutetium. Cerium to lutetium, 14 elements are lanthanoids. But they are coming just after lanthanum, so they are called as lanthanoids. Okay, fine. Okay, so how to write the electronic configuration of them? Okay, actually, we follow this, right? Probably this has been taught to you, 2s, 2p, right? What is this? Afbabu principle, right? 3s, 3p, 3d orbital, and 4s, 4p, 4d, 4f, right? 5s, 5p, 5d, 5f, 6s, 6p, 6d, right? So electrons are being filled according to this, and probably you might have done or know about it. Now, after 4d, this is 5p and 6s. 4d, it is 5p and 6s. After 6s, 4s is to be followed. After 6s, having 2 electrons, it is the 4f to be filled from 1 to 14. Okay, but the lanthanum should have this configuration 4f1 6s2 should be the configuration of this according to Fu principle. But strangely it is having 4f0 5d1 6s2. The electron is in the 5d orbital, therefore it is considered as a d block element and placed it after lanthanum. From cerium onwards, it is kept as a lanthanum, kept as the lanthanoids or that series. Now the 5d, the first itself is the anomaly, lanthanum itself is the anomaly. Then cerium electronic configuration is 4f1 5d1 6s2. This is the two ways that is being written. 4f2 5d0 6s2. This is having 2 electrons in the 4f or 1 electron each, right? These are all the two possibilities of electronic configuration. Okay, so we look into the electronic configuration. Okay, fine, right. So electronic configuration, you can see here. Right. So electronic configuration 5d1 6s2, 5d1 6s2 lanthanum, cerium 4f1 5d1 6s2. Some praseodymium, it is 4f3. It is normalized. It is not pushing the electron to the d. Now, third element is having 3 electrons, 4f4, 4f5 6s2, 4f6 6s2, 4f7 6s2. Up to this, up to europium, the normal electronic configuration. Then gadolinium, when comes to that gadolinium, the 8th electron enters the 5d1. It is not 4f8, it is 4f7 and 5d1. It is because for the half-filled stability, to gain the half-filled stability, this is showing such kind of configuration, right? And then the next element is 4f9. Okay, stabilized again. It is supposed to be 4. It is 4f8 only is done like that, but other things again normalized. Again, in the last case, ytterbium and lutetium. Lutetium pushes 1 electron to 5d1. Its configuration is 4f14, 5d1, 6s2. Okay, so in order to get stabilized or in order to get half-filled stability or full-filled stability, electrons are pushed to the next d orbital. This is the way that gets stabilized. But in case of d block elements, the s electrons are taken. Therefore, chromium is the 4 electrons were there in the d orbital. It takes 1 electron from the s. So this was the case. But here, pushing the electron to the d, the next shell. Okay, this is the way that it is being stabilized. So lanthanoid contraction, it is an important, the gradual or regular decrease of atomic radius, atomic or ionic radius from lanthanum to lutetium. It is called lanthanoid contraction. There is a progressive decrease. We can say progressive decrease. What is the reason for this? Due to the new electrons in n-2f subshell, which shows more poor shielding effect. It is poor shielding effect of 4f electrons. 4f electrons, you can say, right? So particularly it is using 4f. Okay. Lanthanoids use 4f, 5d, 6s orbitals. After the noble gas core, they uses these orbitals, right? What are the consequences of this? Consequences, their separation is difficult. They have small difference in proportion. They have small difference not only between the lanthanoids, also it affects the zirconium, hafnium or the 4d and 5d series of transition elements. Okay, 4d, 5d series of transition elements are also affected. And because of the size is decreasing, lanthanum to lutetium, as the size decreases, this is lanthanum hydroxide is more basic. then lutetium hydroxide, right? Basicity decreases of their hydroxides. Okay, so this is also one of the consequences of lanthanoid contraction. You can see the regular or freehand curve we can write. All forms +3 oxidation state, and there is no exception at all. They form, okay, the regular decrease. They can show the regular decrease, right? So atomic number and this atomic radius change, okay, the radius change about 85, you can take it as 85 to 105, 85 to 105. There is a small variation only, but it is shown in that way. This is the variation as the atomic radius, right? So remember that what is lanthanoid contraction? What is the reason for lanthanoid contraction? Poor shielding effect of 4f electrons. And what are the consequences of that? So this is what you have to write when explain about lanthanoid contraction is being asked. The lanthanoids are highly dense metals. Their density is high. They have high melting point. Okay, so they also show higher enthalpy of atomization and high melting point, and they form alloys easily. Okay, so they are rare, therefore their use is not come to the picture. Okay, now coming to the oxidation state, the lanthanoids show +3 oxidation state as very stable oxidation state. Most common oxidation state of lanthanum is +3. So there is any electronic configuration which is responsible for it. Okay, and they also show +4 and +2 are the another two oxidation state, and they +2 and +4 also, they are formed when they are getting half field stability or full field stability by losing 4 or 2 electrons. When it has to form +4 oxidation state, it has to lose 4 electrons. So by losing 4 electrons, if you get half field stability or F0 configuration, F7 configuration, or F14 configuration, then they show such kind of variable, which kind of oxidation state, right? So cerium, the +3 is so stable that cerium +4 oxidation state undergo reduction to give the most stable oxidation state is +3. Even though cerium +4 is F0 configuration, this show, and it has got it is a good oxidizing agent. Cerium 4+ is a good oxidizing agent, right? So all the elements show exceptionally more stable +3 oxidation state, along with +2, +4 also possible. Along with +2 and +2 are possible in few cases. Okay. Okay. So they are reducing agents. They are good metals, means they are reducing agents. They are electropositive character. The electropositive character and their reduction potential. They have got reduction potential or electrode potential values ranges from -2.2 to -2.4. Right? They also show ability to formation of alloys, and the magnetic property, they are paramagnetic. These things that we can say. Now coming to the chemical reactions. Okay, lanthanum, just like other metals, it reacts with hydrogen, it reacts with halogen, it reacts with water to give hydrogen gas. Okay, strong metal as sodium, it is reacting with water to give hydrogen gas. It reacts with acids, it burns to give oxygen, it heated with form sulfides, nitrites it will form. Okay, so here lanthanides, all elements including lanthanum is denoted as Ln. It's a common symbol for lanthanoids, right? And all in chemical reactions and the chemical products, what are the products which are being formed, they show +3 oxidation state. Suppose if this reacts with oxygen, what you have to write? Ln2O3. Just as aluminium oxide, you have to write, consider for all lanthanum. +3 is the oxidation state, right? Nitride is Ln(N). Sulfide is Ln2S3, just as this. Ln2s3. Okay, with acids they gives hydrogen. Lanthanum gives hydrogen, and with halogen it is Lnx3. So this is the way that it shows chemical behavior. Lanthanoids show chemical behavior like this. There is one use that lanthanoids form an alloy called mixed metal. Mixed metal is an alloy of lanthanoids, which consisting of 95% of lanthanoids and 5% of iron. And this and the traces of sulfur, carbon and all. It is used in tracer belts and shells and lighter flints. Okay, they are pyrophoric. When they are rubbed with the harsh substances, they get the fire, or they will give the sparks, right? Therefore, they are used in these cases. Okay, pyrophoric bullets they are using. Okay, actinoids. Now coming to the actinoids. Actinoids include the 14 elements from thorium to lawrencium. Okay, TH. The actinoids are radioactive elements. Actinoids are radioactive elements. Okay, so their chemical nature, chemical properties of much use. Just for understanding, we are noting down this. That's the only thing. The earlier members have relatively long half-lives, and the later ones have half-life values ranging from a day or 3 minutes. So their half-life period is very short. Okay, they are converted into different other substances. Okay. Now coming to the electronic configuration. Okay, there is no much difference between lanthanoids and actinoids. The same way, whenever it wants to have half-filled stability, it pushes. But there are few exceptions. These exceptions have no meaning or no, it is not being rationalized in anywhere. Protactinium, uranium, and neptunium also shows pushing one electron. Even though they are not stable, they show such kind of electronic configuration. And as it is given in the book like that, we have to believe that it must be so. Okay, thus ionic radii. Even ionic radii, lanthanoids also show regular decrease in their atomic radius or ionic radius, and this is called actinoid contraction. Actinoid contraction is more than lanthanoid contraction. Okay, what we mean that is actinoids, there is more poor shielding of 5f electrons. Lanthanoids show poor shielding because of the 4f electrons, and 5f is more diffused. Therefore, there will be more contraction. We mean more contraction when it is actinoid contraction. Actinoid contraction is greater than lanthanoid contraction due to poor shielding effect of 5f electrons than 4f electrons. It is given. Oxidation states. Here is the difference. Lanthanoids show +3 as common oxidation state and +4 and +2 in few cases. But actinoids show up to +7. Up to +7. So these are the oxidation states of various elements. +3 is commonly present, and neptunium, plutonium will show up to +7. Okay, they show more variable oxidation states. It may be because of 5f and 5f 6d 7s. These orbitals, these are closer. These are quite closer. Rather in 4f 5d 6s in the lanthanoids, because actinoid contraction is little more, the orbitals are nearer, the movement of electrons from one orbital to another orbital is more easily possible. Therefore, they may show the variable oxidation state as such. So they show magnetic properties. They are strongly paramagnetic. Okay, they are strongly paramagnetic, and density, they are showing the they are dense metals, or density also is like the metals, they have high. Ionization energy, they have low ionization energies. I mean, they are better metals. Reducing agents, actinoids are strong reducing agent, and they are highly electropositive elements. Okay, as usually that we are taking from the same way as that of lanthanides. Okay, what are the difference between these two? At this point of time, it is better to know. 4f orbitals are progressively filled here in the lanthanides. 5f orbitals are filled. That is the difference. Common oxidation state is +3, +2, +4. Actinoids show along with +3, +4, +5, +6, +7 also. And except promethium, they are non-radioactive. Only promethium is radioactive, lanthanoids. But actinoids all are radioactive. So this is a difference. And the compounds of lanthanoids are less basic. Actinoid compounds are more basic, but is more strongly metal. Actinoids are more strongly, they are metals. Okay. And actinoids show more ability to form complexes. Right? More ability to form complexes. Now I have collected some questions of the sample paper 2023-24. Right? So these are the questions. These are the questions which are asked. In the sample paper. Let you look into this, whether you can able to say the answer to that or not. And surprisingly, they have given this element Ne5. Okay, 5-mark question with 7 questions. I think 1, 2, 3, 4, 5, 6, 7. 7 questions out of this 5 are to be attempted. Right. Which of the following ions will have the magnetic moment value 1.73 bm, Bohr's magneton? Scandium 3+, titanium 3+, titanium 2+, copper 2+, zinc 2+. Which out of this is having magnetic moment of 1.73? Magnetic moment is found out by the formula root of n into n plus 2, where n is the number of unpaired electrons, right? Where n is the number of unpaired electrons. Suppose this value is 3. Sorry, suppose this value is 1.73 as it is given. 1.73. What should be the value of n? Okay, 1.73. Okay, 1.73 is nothing but square root of 3 value. Square root of 3 value. Square root of 3 means this should be 1, 1 plus 2. N should be 1. Then only this can be square root of 3. Correct? N is equal to 1. 1 plus 2 is 3. Now that means there must be one unpaired electron. Which species is having one unpaired electron? You have to see. That's only the thing. Simple only, but you have to work out all these things. Right? So titanium 2+, right? Scandium 3+ is D0 configuration. Titanium 3+, I think titanium 3+ is having 1 electron. Yes. Titanium is 22 electron. This is 3D2, 4s2, titanium. And whenever titanium 3+ is there, it has to lose 2 plus 1. Yes. So titanium 3+. Titanium 3+ is the one which is having mu value 1.73. Right. Second one, in order to protect iron from corrosion, which one will you use, will you prefer as sacrificial electrode? Nickel or zinc? And why? They have given another information. Given standard electrode potentials of nickel, iron, zinc are this. Okay. They have given the reduction potential values. Okay. Now, always the coating of the metal is to be done by more reactive metal so that it can coating or protect from the corrosion or what for sacrificial protection, whatever it is, it should be more reactive metal, right? If it is less reactive metal, if it is cut, if it is simply the layer is open, then it is get rusted more. Now, if it is a zinc is more reactive than iron, therefore zinc coating is being done. So you can say this is iron and it has got more negative value, zinc. Therefore, this is being taken. It has got less negative value. Okay. Therefore, it is less reactive, nickel. Therefore, we do not use nickel or copper for the protection of iron. Okay. This is how we have to explain there. The more reactive metals are being coated because they will stop corrosion by supplying electron at the cost of themselves. right? Zinc coated means zinc will send its electron and zinc will become oxide. Zinc form its oxide. But zinc oxide will not become hydrated. It becomes do not form a flaky thing and it won't fall down. It will be adhering to the iron metal itself. Okay. The second ionization enthalpy of chromium and manganese are 1592 and 1509 kilojoules per mole respectively. Explain the lower value of manganese. Explain the lower value of manganese. Second ionization enthalpies of chromium and manganese. Okay. So chromium is 3d5 4s1. When you want to take out two electrons, because second ionization energy is asked, if you take out one electron, it is d5 configuration. If you are taking another electron, you should choose from one of the 5 electrons which is already in stable form. Therefore, whenever you are disturbing the stability, it needs more energy. But manganese is having 3d5 4s2. So 2 electrons are lost, it gains stability only. Therefore, the manganese is having lower IE2, IE1 and IE2. Sum of that. Yes. Give two similarities in the properties of scandium and zinc. Two similarities in properties of scandium and zinc. Right. Scandium, zinc, both salts are colorless. Because scandium is because of the D0 configuration, zinc is because of D10 configuration. That is one thing. And both scandium salts and zinc salts are diamagnetic. You can say diamagnetic also, because no unpaired electron is being present. Right. What is actinoid contraction and what are the causes of actinoid contraction? Just as discussed, this was the question there. What is the oxidation state of chromium in chromate ion and dichromate ion? Chromate ion and dichromate ion. Oxidation state. CrO4 2 minus. Cr2O7 2 minus. Okay, this is chromate ion, this is dichromate ion. In both the cases, it is +6. In both the cases, it is +6. But in the case of manganese, it is not so. Manganate ion, permanganate ion, their oxidation state is different. One is +7, another is +6. But in chromate ion and dichromate ion, the oxidation state is +6. Write the ionic equation of reaction of Ki with acidified KMnO4. Write the ionic equation of reaction of Ki with acidified KMnO4. This is the way the questions are asked. So you should know that MnO4 minus plus H plus, right? With some electrons, it will give Mn2 plus. MnO4 minus permanganate ion will give Mn2 plus. And iodide ion, Ki, iodide ion is present here. Sorry. Iodide ion is present here. This iodide ion is converted into I2. So they give like this, Ki with KMnO4, right? Iodide ion is converted into this. Okay. I2. Iodide ion is I2. So this is the equation that you have to write. And that is the way, that's how you have to. And here, any phi is being asked, you will get some option. If it is given in that way, it is good if it in that way. Okay. So all examination, what you are seeing is questions are splitted into 1 mark. You need not elaborately write something. There is nothing like derivation or elaborately write or proving anything. But your work should be specific. Your answer should be very specific. That's how in chemistry paper, there is no lengthy question. But each small thing you should understand to the perfection level. Then only you can able to
Hello. Hello.